Welcome back, students. This is the session 7 from the playlist of current electricity, and the topic for this session is the series and parallel combination of resistors. So here I have already drawn one diagram in which in the first diagram, that is in this diagram, there are two resistors which are connected in series, and in the second diagram there are these two resistors which are connected in parallel, and these resistors are then connected to an external voltage source as shown in this figure. Now in the series combination, the current through each of the resistor will remain the same, and the potential difference across the ends of the this series combination will be given by V is equal to V1 plus V2, where V1 is the potential difference across this resistor R1 and V2 is the potential difference across this resistor R2, and this is the external voltage source having the value of V. So here I have assumed that the current which is flowing in this circuit is I. So if the equivalent resistance of this circuit is R, then we can write this equation as V is equal to IR, and this will be equal to, now V1 is equal to what? That will be equal to the current in both the two resistors will be the same. So V1 will be equal to I R1 plus V2 will be equal to I R2. So from this relation we get that the equivalent resistance of this circuit, or you can say the equivalent resistance of a series circuit, is equal to R1 plus R2 and so on. So in this case, since there are only two resistors, therefore the equivalent resistance is equal to R1 plus R2. But if there are more than two, let's say there are n resistors, then the equivalent resistance will be equal to R1 plus R2 plus R3 and so on up to Rn. So now in the case of a series circuit, the potential difference across the two ends of the series combination will be equal to the sum of the potential difference across each resistor. So this is the first point which has to be remembered, and based on this concept we have been able to find the value of the equivalent resistance in the series circuit, which is equal to R1 plus R2 plus R3 and so on. Now let us come to the second combination, that is called the parallel combination. So in the parallel combination, here the voltage, the potential difference across each resistor is the same. So this is this R1 and R2 are connected in parallel, and this combination is connected to the external voltage source. So if the current in the circuit is I here, see here the current which is flowing in the circuit is the current in this that resistance R1 is I1, the current in this resistance R2 is I2, and the total current which is flowing in the circuit is I. So here I will be equal to I1 plus I2, and in the parallel combination the potential difference across each resistor is the same. So if the so I is equal to I1 plus I2, now I can be written as V upon R, where R is the equivalent resistance of this parallel combination, and I1 will be equal to V upon R1 plus V upon R2, since the potential difference across each resistor is the same. So from this equation we get that 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2, and if there are n resistors in the parallel, if there are n resistors which are connected in parallel, then this equation can be written as 1 plus R1 plus 1 plus R2 plus 1 plus R3 plus 1 divided by plus up to 1 divided by Rn. So in the parallel combination, the equivalent resistance is given by 1 divided by R equivalent, which is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. In the series combination, the equivalent resistance is given by R is equal to, this is the equivalent resistance, this is equal to R1 plus R2 plus R3 and so on. In the series combination, the potential difference across the series combination, across the two ends of the series combination is equal to the potential difference, is equal to the sum of the potential difference across each resistor. So V is equal to V1 plus V2 plus, it can be up to Vn, where n is the number of resistors. So and in the case of the parallel combination, the potential difference across each resistor is the same. So based on this concept, we were able to find this relation, and so these were some of the important points which I wanted to discuss in this session. And in the next session, I will be taking up the another topic of Kirchhoff law, where we will be discussing about the loop rule and the junction rule. So thank you very much for joining this session, and have a nice day. Bye.